drawing Lewis dot structures of various compounds. So we've already looked, you should know how to draw a Lewis dot structure. You might know it as an electron dot diagram. They mean the same. So the key concept to know when drawing any Lewis dot structures is being able to identify the valence electrons, right? When drawing, right, we want to draw our valence electrons of our structure. So let's take, for example, any element on the periodic table. So let's take something like oxygen, right? So when drawing a Lewis dot structure, we start off with the symbol, okay, just to kind of give you a little review on how to draw a Lewis dot structure in an electron dot diagram. Start off with a symbol, and then imagine, okay, imagine, and I'm going to do it with red, imagine a box around the symbol. And on each side of the box, you're going to draw your electrons. So in oxygen, we've got 6 valence electrons. So what we're going to do is we're going to start at the top. I like to start at the top. 1, and we're going to draw electrons, 1 on each side of the box. Right? So now we've filled up the box with 1 electron on each side. After we've drawn 4 electrons, then where do we draw our 5th? That's when I start to pair up the electrons. Mind you, this red box that I've drawn in, think of it as an imaginary box, right? We don't really draw it, and eventually we want to accustom ourselves to know how to put this together without drawing in the box. And so these are the valence electrons. And the reason why I like to draw it this way is because when we're drawing structures of a compound, we want to identify these electrons that have not been paired up. So this electron that's not been paired up, this electron that's not been paired up. And these electrons that have not been paired up is what I like to call a bonding site. So if we're drawing a covalent compound or a molecular compound, right? So we're looking at 2 or more nonmetals, and then we're just kind of, I'll remind you about that in just a second. That would be the bonding site in which the sharing of the electrons will occur at. Okay, so let's look at a few things, a few other rules pretty much when drawing these compounds. So first, identify metal, non-metal. Really, really important, right? Because this is going to determine how we are actually going to draw our structure. Next, if we have a metal or and a non-metal, right? So if we have a metal and a non-metal, we have what we call an ionic compound. And with ionic compounds, key word here being ion, so we know we're going to have charged atoms. Right? So charged atoms, we're going to have a positive combined with a negative, right? So metals, if you notice in the periodic table, metals become positively charged, non-metals become negatively charged. And how do they become? Well, as you should know, metals usually give up electrons to these non-metals. And finally, the last one to look at is if we have 2 or more non-metals, this is what we have when we have a covalent compound or a covalent bond. And with covalence, these deal with the sharing of electrons. Okay? So we're going to share electrons here between 2 or more non-metals. So there's no gaining, there is no losing of electrons whatsoever. If you don't know that by now, then you shouldn't be continuing on this. Go back and actually do look over the rules for covalent and ionic compounds. So let's look at the first example. Draw the compound CCl4. So with this compound, when we're putting this together and drawing it, what I like to do is I like to start off with one of each, so, or with at least, the one lonely carbon, and we've got 4 chlorines with it. So what we do is we start off with carbon, let's say, and I'll draw chlorine as well. Let me draw chlorine actually with a different color, just to show the difference. So we'll draw chlorine as such. So we're going to start off drawing, so I like to start off with both of them, kind of side by side. And what we're going to do is we're going to draw the valence electrons around carbon. So carbon's got 4 valence electrons, 1, 2, 3, 4. Notice how they are all on their own. We've not paired them up. Right? So, because as I stated at the very beginning, when they are by themselves, we consider these bonding sites. Bonding sites. So each of these lonely electrons are considered a bonding site, which means it's a location in which a bond will occur, right? So a pairing will occur with another atom. So we've got 4 bonding sites, right? 1, 2, 3, 4. Right? So let me color them back in blue. Right? So those are the 4 bonding sites because they're all 4 lonely electrons. Then we're going to draw the valence electrons for chlorine. Chlorine has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. Okay, so now we're looking at these 2, right? But more importantly, what was really important to identify is, well, what's going to happen? Is carbon going to gain or lose electrons, right? So it's really important that even before we start drawing these, we should identify the fact that both of them are nonmetals, right? They're both nonmetals, which means we are going to share electrons. Okay? So we're going to share electrons until we form a stable octet with all the atoms. So they've pretty much fulfilled the maximum number of electrons that they can possibly fill up, with the exception of, let's say, hydrogen, right, and the atoms that are close there, which can only require only 1 more electron to become stable. So it doesn't fulfill the octet in terms of 8 valence electrons, but it will be 2. But don't worry about that. Let's worry about this example here. So, remember how we said the bonding site is the one that's by itself. Chlorine has only 1 bonding site. Okay, so it's got only 1 bonding site. So the rule is, when we're drawing these electrons, usually, pretty much, well, the central atom is usually the atom that has the most bonding sites. And that would be carbon in this example, right? Because if we look at chlorine, chlorine needs 1 more electron to become stable. It's only got 1 bonding site. So once it shares an electron, as it will here in this example, so we're going to share that electron, that's it for chlorine. Chlorine has the 7 of its own electrons, plus this one that it's sharing 8 electrons. Carbon, on the other hand, has 4 of its own, plus this one that it's sharing with chlorine. It's got now 5, which means it needs to bond 3 more times. And what's left over? Well, we've got 4 chlorines, we've got 1 accounted for, which means you can almost assume where the other chlorines will be. Right? When drawing them, I try to stay with some kind of geometric shape, right? Straight line with atoms, right, on either end. Sometimes we might go in a cross formation. Okay, so these are shapes that we try to keep in mind. Sometimes you might have a T shape, let's say, in that form, or in this form. Let's say if you've got only 4 atoms. Okay, so in this one we've got 5 atoms in total, so we try to keep it in like a cross shape when we're actually drawing it. So let me erase some of this stuff so we can have room to put, okay, some of the information here. So we've got already the 1 bond, okay, that we've created between 1 chlorine and our central carbon. And as we said, the central carbon is there because it is the atom that has the most bonding sites. So what I like to do is, I always like to draw my other atoms, my outer atoms, okay, in the location that are pretty much in line with these bonding sites. Okay, so let's draw 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. I'm going to draw them all the same way. And eventually, with more practice, you'll understand where you can. It doesn't really matter. Like, notice here, I've got my lonely electron here, my bonding site there, which is probably not the best place to put it, considering that I'm going to form a bond with the central chlorine. Right? So you can get into the habit, if you know how many valence electrons you've got, right? So we're going to put. What I'm going to do is, instead of pairing this one up here at the top, I'm going to pair this, 6, and number 7. So what I have is I've got the bonding site here pretty much located in the same direction of my other bonding site. Right? This chlorine, 1, 2, 3, 4, 5, 6. I don't have to pair this one, but I'm going to do it here instead, just for argument's sake. Right? So I've drawn my 4 chlorines. Right? Let me get rid of this line right here. Okay? And what we're going to do is we are going to pair up the electrons, right? The lonely pair. So we've got a pair here. They're going to pair up. So a bonding site is, they're meeting together. So a bonding site from one atom meets with another bonding site. This one here is going to bond with its bonding site, right? Notice how it gets kind of messy, but I'm going to show you guys how to clean it up. Now look at this one here. We've got this electron here. We've got that electron there. So what we're going to do is we're going to bond it this way. Right? So now that kind of looks messy, right? You're not going to hand that into your teacher and say, look, here it is. Here's all the bonding, for between chlorine and these 4 chlorines, right? This carbon tetrachloride. So what we do is we try to clean up the diagram. So this is your scrap work. So in your good work, what you're going to do is you start off, but actually we're going to start off with our central atom. Right? Now another thing to keep in mind, actually, one thing I should have mentioned is you want to double check that all the atoms, let me see how we did this 8 here, we've noticed, right? So what we want to do is we want to make sure all of them have the 8 electrons, or they have a full valence shell, so to speak, or sorry, a full valence octet, that they fulfill the octet rule. So this chlorine here at the bottom has 7 of its own electrons, plus this one, 8 electrons. This chlorine over here on the left, 7 of its own, plus this one that is sharing, 8. This chlorine, same thing, 8. Let's see this carbon now in the middle. This carbon has 4 of its own, right? We've drawn them in with blue. But it's sharing one of these black electrons here. So that's 5. This one, 6. This one, 7. And this one, 8. So all the atoms have 8 valence electrons, whether they're their own or it's the ones that they've shared. Okay? So now, when we're simplifying our drawing, like I said, try to keep that geometric shape going, right? We said we're going to draw it in a cross form. So we look at carbon, and carbon is bonded once with 4 chlorines. So we've got 4 chlorines. So to simplify this whole thing that we've done, we simplify it by drawing a straight line. That straight line shows me that I've got a bond, one single bond between that carbon and the chlorine, right? So each line represents 2 electrons. And imagine it as if there was 1 and 1 on either end. And that's how the sharing goes, right? So we've got a bond there, we've got another bond here, we've got another bond here, and we've got another bond here. So right now in the center, this carbon has 2 electrons here, 2 electrons with that line, 2 electrons with this line, 2 electrons with this line, which shows me that carbon has 8 electrons, 8 valence electrons. Now the chlorine has got now the 2 that are showing. What we need to show now, and I don't know, you check with your teacher if they want you to show them, is to show the extra pairs, the shared pairs of electrons. And notice how each chlorine has 1 shared pair, a 2nd shared pair, and a 3rd shared pair. And then just fill those in with all of them. Okay? And there you have it. There is our Lewis dot structure of carbon tetrachloride. Okay, so let's look at a couple of other examples. Let's look at this one. Draw the compound nitrogen tribromide. So again, what I like to do, first thing is first, identify non-metal, non-metal. So we know that the bond forming here is covalent and that we are going to share the electrons, okay, until we have what we call the stable octet. So I like to start off with drawing one of each. So we've got a nitrogen and we've got a bromine. Okay, so draw the valence electrons for nitrogen. Nitrogen has 1, 2, 3, 4, 5 valence electrons. Bromine has 7. 1, 2, 3, 4, 5, 6, 7 valence electrons. So if you look at, we've got 1 bonding site. Nitrogen has 3 bonding sites, right? Which means nitrogen will be the central atom. Okay, so nitrogen will be the central atom. So let's get rid of the red and just redraw in our bonding sites. So what we're going to do is, in line with these bonding sites, we are going to fill in the remaining 2 bromines, right? Because remember, we start off, we've got 4 atoms in total, but I'm only going to draw 1 of each atom, right? That's all I have of nitrogen, but I have 3 bromines that need to be accounted for. And if we draw 1, I'm only accounting for 1 of them, which means I got to account for 2 other ones, right? So again, 1, 2, 3, 4, 5. I'm not going to pair this one. I'm going to pair this one 6, this one 7. Because what I want is, I want the bonding site that's going to occur to be in line, right? It keeps things a little bit cleaner. Okay, here at the bottom, 1, 2, 3, 4. I'm not going to pair that one. I'm going to pair that one 5, 6, 7 valence electrons, which will allow this pair to occur. And finally, we've got that pair. So let's go double check that everything's got 8 valence electrons. So this nitrogen in the center has 5 of its own, plus this one, 6, plus this one, 7, plus this one that is sharing 8. So nitrogen has 8 valence electrons surrounding it. Each bromine has 7, plus 1 that it's sharing, which means all the bromine have 8 valence electrons. So, how do we simplify this? Well, again, start off with our central atom. We have nitrogen. It's bonding 3 times, 1, 2, 3, to bromine, bromine, bromine. So this line, as I said before, represents this circling of the electrons. So we don't show that. It becomes messy, becomes, there's way too much. Now the only thing that's left is draw in these shared pairs of electrons. Nitrogen has 1 shared pair, right? Each bromine has 3 pairs of shared electrons. Okay. And you can always double check how many, just to make sure that you've drawn 8 electrons, right? So we've got the 2, right? So around bromine we've got 2, 4, 6 electrons, and remember, each line represents 2 electrons. So we've got 6, 7, 8. Each one has got 8. This nitrogen has the shared pair here at the top, and each line represents 2, 4, 6, plus this 2 gives it 8 valence electrons. Okay, so pretty much really, really simple when putting together these structures. Draw the compound H2O. Right? Now, here's the thing. Do we want to identify metal, non-metal? Yes, we do. But here, one thing that might give some problems is the H. And H is located on the metal side, but hydrogen is very funny. It pretty much acts as a non-metal. And we treat it as a non-metal, so it's going to share electrons. So, which means, now, if we draw, we're going to draw one of each. We're going to draw hydrogen, and we're going to draw oxygen. So now, hydrogen has 1 valence electron. Oxygen, on the other hand, has 6 valence electrons. 4, 5, 6. Oxygen has 2 bonding sites, hydrogen 1, which means, where am I going to put the other hydrogen? Well, I'm going to put the other hydrogen pretty much on the other end. I'm not going to put it here because if I was to share these electrons, there is no room now to get these electrons to be shared. Now, another thing. Let me show you guys when putting together, another reason why when we're pairing up these electrons, remember how we said we draw one and we don't pair them up? Because if we pair them up, right, I've got now technically 6 valence electrons around oxygen. Drawing it this way now makes things difficult when we're pairing up or when we're showing the bonding sites. Because remember, according to the rules, the way I've been trying to explain it to you, by drawing the single electron, right, by not pairing them up until after 4 valence electrons, it gives me something to know where there's a bonding site. And of course, some rules kind of break the rules, and we're going to see that towards the end with a few exceptions to the rule. So, what we want to do is we want to make sure that we always draw them the same way I showed it to you guys. 1 on each side, and then after number 4, electron number 5 gets paired, electron 6 gets paired, and then electron 7 gets paired. Right? Just because now I'm showing 2 bonding sites. The other way, I didn't show them. Right? So we've got 2 bonding sites. Right? Hydrogen has 1 valence electrons. Another rule, remember, hydrogen is always to the outside of the atoms. Right? Because hydrogen just needs 1 electron to share with. Right? Once it's shared, that's it. It's done. Right? So you never bond it really immediately with something. It's always usually to the outside of your central atoms. Okay? So we know oxygen is going to be the central atom. So we're going to share this electron. So they're shared. That's done. Now this hydrogen is going to share with this oxygen bonding site. And pretty much now let's double check. So oxygen has 6 of its own valence electrons, plus this one, 7, plus this one, 8. So oxygen has 8 valence electrons. Hydrogen, on the other hand, has 1 of its own, plus this one that it's sharing. It has a maximum of 2 electrons that it can possibly hold in its pretty much only energy level. Okay? So hydrogen is one of the exceptions to the rule, to that octet rule. Its octet is 2 valence electrons. Right? So how do I simplify this diagram? Well, I start off with my central atom. This oxygen is bonded once with a hydrogen. It's bonded once with another hydrogen. And then I fill in my unshared pairs. Right? So my shared pairs. So I've got 1 pair, and let me put the other pair on the other side. For argument's sake, it doesn't really matter. I can put them both on the same side. It doesn't really matter. It will matter if you're drawing what we call Vesper diagrams, or following the Vesper theory to identify the shape of this structure. But if you're just looking to put together just a simple Lewis dot structure, that will suffice. Draw the compound HCN. So we've got 3 atoms. Right? One thing to keep in mind, when you've got carbon, carbon has 4 bonding sites. So carbon will always be our central atom. So we've got carbon, 1, 2, 3, 4 valence electrons. So what I'm going to do is I'm going to draw a hydrogen on this side. I'm going to draw my nitrogen on this side. Nitrogen has 5 valence electrons. 1, 2, 3, 4, 5. It's got 3 bonding sites. So what's going to happen is, in this one, hydrogen is going to bond once with carbon. And that's it. Hydrogen is done. Now, carbon has 3 bonding sites. So does nitrogen. So what's going to happen is, they're going to bond to one another. Each single or each bonding site is going to partner up with one another. Right? So we have something different here. we've got carbon bonded to nitrogen 3 times. So when drawing this, when simplifying this diagram, we start off with our central atom, which is carbon. Carbon bonds once with hydrogen. Carbon is going to bond 3 times with nitrogen. And we have 1 pair of electrons still left to draw. We can draw them there, we can draw them on the side, we can draw it below it. Doesn't really matter. But now let's double check. So remember what we said, each line represents 2 electrons. Surrounding carbon, there are 4 lines. Each line represents 2 electrons, so we have a total of 8 electrons. Hydrogen can only fit 2, so it's got the 1 line, so it's got 2 electrons. Nitrogen has these 2 electrons, plus each line, 3 lines, to give it a total of 8 electrons. So all of them fulfill the octet rule. So this is the, and this is one of the trickier ones that you'll get at the junior level, probably of drawing. We will go into some of the more detailed polyatomics towards the end. Now let's look at the following example. Draw the compound NaCl. So what's unique about this example is when you look at the periodic table to identify metal, non-metal, we actually have a metal and a non-metal. So when we have a metal and a non-metal, this forms what we call an ionic compound. In ionic compounds, right, we have pretty much we form ions. So metals, to form ions, they will lose electrons. Non-metals will gain those electrons. And there's an attraction between the positive and negative charges of these ions. So let's look. So again, when we're drawing the actual Lewis dot diagram or the electron dot diagram of each one of these atoms, well, we start the same way. NaCl. So we draw Na as, or sodium has 1 valence electron. Chlorine has 7 valence electrons. 2, there's 3, there's 4, there's 5, there's 6, and there's 7. So for sodium to become stable in an ionic compound, it has a tendency to want to lose that 1 electron. For chlorine, because it's a non-metal, they want to gain the electrons to become stable. So what's going to happen is sodium is dying to get rid of this 1 electron. Chlorine is dying to pick up 1 electron. So they kind of work mutually together. So sodium is going to give up the electron to chlorine. So when sodium gives up the electron to chlorine, sodium becomes positively charged. Chlorine, on the other hand, has picked up an electron. So we've got 1, 2, 3, 4, 5, 6, 7 of its own valence electrons, plus the 1 it picked it up, and I'm going to show it with a different color, just to show that this is not the original electron that was there. Right? So it picked up an extra electron, so it becomes it becomes negatively charged. It becomes a -1 charge. And now we have an attraction between, right, the cation, right, the cation, that's what we call metals that have become positively charged, with the anion, right, which are the nonmetals that have become negatively charged. So there's an attraction. So how do we finish drawing this? Well, we put square brackets to separate them. But we know that there's an attraction between these 2 atoms, or these 2 ions now. Okay? Note the difference between ionic compounds, right, when we're drawing them. Notice how we're not circling any of the electrons. We don't care about bonding sites. The only thing we know is with this lone electron here, that's where this electron is going to want to pair up with. Right? So they're not sharing the electrons, they're actually, one's giving it up, the other one is picking it up. Okay, so when we're drawing these Lewis dot structures for ionic compounds, don't forget the square brackets. Sometimes, find out from, I guess, your teacher, right? Sometimes they will include the symbol in the square brackets, and they will put the charge to the outside of the square bracket. So again, find out from your teacher, right? And remember that you're including the electrons. And like I said, I like to use a different color to show the added electron. And so now, and again, same thing, we've got the charge that's going on between the Na with the Cl, and that's how this bond actually forms. So again, like I said, when drawing it, double check with your teacher what they want in terms of where they want you to put the positive and negative charge of the ionic compound. Next example. Now, I'm not giving you the formula. I'm actually giving it to you in terms of names. So we are going to combine here. So we're going to draw a compound that contains lithium and oxygen. Okay. Now, nowhere in the formula does it tell us how many of each one we've got. But we always start off with one of each one of these atoms, and we work that way. Right? So, first off, we want to identify metal, non-metal. Well, we look at lithium is the metal. So right away, because I know we've got a metal, we know it's got to be ionic, right? And the other one's non-metal. So we know this compound is going to be ionic, right? So ionic means, in the end, when we're drawing it, we want to have the square bracket. So first off, we are going to start off with our metal. Right? So start off with our metal, lithium. Lithium has one valence electron. Oxygen, and let's draw a different color. 1, 2, 3, 4, 5, 6 valence electrons. So, what's going to happen? Well, lithium is going to give up that electron, right? Remember, metals give up the electron to nonmetals. So lithium is going to give up the electron, and lithium is going to be positive 1 charged. Now, it's going to bond next to an oxygen, right? We know it's got the oxygen, right? We've got 1, 2, 3, 4, 5, 6 of its own electrons, plus this one that it's taken, 7 electrons, which now technically makes this oxygen negative 1 charge. But if we look at it, oxygen is still not stable, right? So once we get rid of this electron and it's gone here, we've got room with this 1 electron, which means what do we need to do? Well, nowhere in the question does it state how many of each one we have, which means oxygen now is the only thing that is left to become stable. So for oxygen to become stable, it is going to require the electron of another lithium. So this lithium is going to give off the electron. So using this method here, we can figure out almost what the formula is. We could actually figure out the formula using the crossover method between lithium and oxygen. But there's another way of figuring out, if you're given a question like this on a test, to figure out what is the actual formula that is formed between these two. So which means if we've got another lithium, we're going to put another lithium in here. It's given off that electron, so it's positive 1. This oxygen has picked up another electron. It has picked up a total of 2 electrons. So this oxygen will now have a negative 2 charge. So the formula with this, or the formula that we can create after we combine a lithium and an oxygen, is, well, we need 2 lithiums for every oxygen we form. And so the formula for this will always be lithium oxide, and it'll be Li2O. That for every 1 oxygen, we need 2 lithiums, because each lithium is going to give up 1 electron. Oxygen needs 2 electrons to become stable. It will pick up 1 from 1 lithium, pick up another from another lithium. Okay? We could have added another oxygen, but it wouldn't work the same way between the oxygen and the other oxygen. Right? So we had to put another metal that would give up an electron to pair up with this lonely electron that still needed to be bonded with, or sorry, needed to pick up a pair. Okay, that needed to pick up another electron from. Okay, and again, we're not just going to randomly pick any other metal. But Because if we're combining lithium with oxygen together, remember odds are there's going to be more than one lithium available to this oxygen. Okay, so here is what the formula will look like in terms of your Lewis dot structure. Again, remember, ionic compounds, don't forget the square brackets. And again, like I said, include the charge, right? Because that's what's keeping them together. And note, I will not put the two lithiums side by side like this, because these two lithiums here are both positively charged, so they're going to repel one another, right? So make sure that when you're putting your second lithium into this, into this structure, that you're putting it another positive on the negative side, right? We could have drawn it up on top here. We could have drawn it at the bottom. It doesn't really matter, but we could not draw the two positives side by side. Now, here is where things get a little bit trickier. How do we draw the following compound? This is what we call a sulfate. It's a polyatomic, SO4, and it's a -2. So no, you're not seeing something you shouldn't be seeing. It's not a speck on the board, right? That -2 represents that's the charge, right? So now, we've got sulfur, and we've got oxygen. So when we've got this formation, we've got the S, and there's 4 O's, treat the one atom, right? So we've got our non-metal, so we know they're going to share electrons. So what we're going to do is we're going to treat the one that's by itself, right? The atom that's only represented once, with 4 atoms of another. We're always going to treat it as if that S, that lonely atom, is the central atom, which means sulfur is going to be in the middle, surrounded by 4 oxygens. So if you look at the periodic table, sulfur and oxygen, okay, they both have 6 valence electrons. So let's draw them in. 1, 2, 3, 4, 5, 6. Right? So each one, 1, 2, 3, 4, 5, let me do it right here. 6. 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, 6, and the last one. 1, 2, 3, 4, 5, and I put that one there. 6. So now we start off having drawn the electrons, right? The electron dot diagram. We start off again arranging it, right? Our central atom with the most bonding sites. Now, because we've got the 1 sulfur and we've got 4 oxygens, odds are the sulfur is going to be in the middle. Okay, there are other reasons for it, but I don't want to go through those other reasons. But sulfur is right in the middle, surrounded by these 4 oxygens. So what's going to happen now is the following. One thing we have to take into account is this -2. Now, this -2, right, means that I'm going to have to add 2 electrons, right, because -2 means I have 2 extra electrons, and I'm going to add those between the 2 atoms, between sulfur and oxygen, to the atom that is most electronegative. Okay, so my juniors who've never been taught electronegativity, don't worry about this. This is more for the seniors who have been taught the electronegativity and have it on their periodic table. So you look at the periodic table, the one, one that actually states the numbers, and you'll find that oxygen is slightly more electronegative. So what we're going to do is we're going to add 2 electrons. And what I like to do is I like to separate them. I'm not going to give any one of the oxygens all of them. So I'm going to just give randomly 1 electron there, and I'm going to give the other one here. Which means now what I'm going to do is I'm going to pair, right, the oxygens, or sorry, the oxygens with the sulfurs that have not been paired up, right? So what I'm going to do is I'm going to bond this pair. I'm going to bond this, And now I'm stuck, right? Now I'm stuck. Now, if I look at this, I look at it and go, well, I've taken the bonding sites away from, I bonded up with the bonding sites of sulfur, and now I have nothing left. Do not, and I repeat, do not start to bond the oxygen's bonding sites with one another. They will still bond with sulfur. Sulfur is one of those exceptions to the rule. Sulfur is one of those atoms that can form what we call an expanded octet, which means these pairs, right? These pairs here, they can separate from one another and form bonding sites. Okay, so this is one of the exceptions to the rule. We have to create bonds somehow with this formula, right? It's one of the ones that we're given. So what we do is we are going to separate them, and we're going to form bonds, right, with a pair, right? This oxygen needs to be paired up, right? This oxygen with that sulfur needs to be paired up, right? But now we have one more here. And now it's starting to get a little bit messy. Maybe the way I drew it should have been a little bit different. So what we're going to do is, since this pair here, okay, on the right side of sulfur, I've separated that pair. So what I'm going to do is I'm going to move that electron, let's say down here, just to kind of make it a little bit cleaner. And I'm going to form a bond here. So now, how do I simplify this? So sulfur is one of those exceptions to the rule. Another exception to the rule is phosphorus. Right? You'll see phosphorus as a phosphate works the same way. It forms what we call that expanded octet rule, which means I can have more than 8 valence electrons surrounding sulfur. Right? So if we look at it right now with sulfur, sulfur has 1, 2, 3, 4, 5, 6 of its own valence electrons, plus this one 7, 8, 9, 10, 11, 12. So sulfur can have as many as 12 valence electrons. Okay, so it's like a hypervalency. Okay, so it's gone through that, what we call that expanded octet. So now, how do I simplify this diagram? Well, I'm going to do the following. Again, we start off with our central atom, which is sulfur. Sulfur is bonded to oxygen. Right? So it's bonded to oxygen. So these two side oxygens, the one on the left and the right of the sulfur, is bonded once. So we're going to bond it once. The sulfur with the top oxygen is bonded twice. The sulfur with the bottom one is also bonded twice. Right? Now, all we got to do is put in our pairs of electrons. So we've got 1, 2, 3 pairs around that oxygen. So we're going to draw those in. So 1, 2, 1, 2, and my third pair. Right? Now, the oxygen on the right side of it, same thing. Here's one pair, another pair, another pair. So one pair, our second pair, and our third pair. But now don't assume that it's the same thing for the other two oxygens. Remember, these two oxygens that are shown in these pairs are only single bonded to the sulfur. The top two oxygens, the top and bottom oxygen, are double bonded. And notice now how many pairs of shared electrons they've got. 2 pairs each. So 1, 2, 1, 2. So that's 2 pairs. 1, 2, 1, 2. So now what we can do is actually go and count, right? If you look at this oxygen here to the right, the rightmost oxygen, we've got 3 pairs of shared electrons. So that's 6 plus this line represents 7, 8 electrons. This oxygen on the furthest most to the left of this diagram, also 8 valence electrons. Let's look at the top oxygen. This top oxygen has 2 pairs, 1 pair, 2 pairs, plus 2 lines that are bonding. So 2, 4, 6, 8 electrons. The bottom one also has 8 electrons. The only one that doesn't follow that 8 valence electron rule is the one that can have what we call the expanded octet. And sulfur here has 12 electrons. So be really careful when you're drawing these polyatomics, right? Make note that because we have this -2, it means we are adding 2 electrons. Whom are we adding them to? We are adding them to the most electronegative atom in that polyatomic, right? So in that formula. So we look at the periodic table, one that actually has the electronegativity numbers, and we look at the one that's most electronegative, okay? And we put 1 electron in each one of those, right? And then you bond. And keep in mind for these, what we call these expanded octets, because they will allow you to separate paired electrons to fit, right? And if you separate them, remember that they will react to being that expanded octet. Okay?